Okay, we come here to the last topic of the summer homework in the second half of assignment 5, where we're looking at momentum. So number 18 is one we'll look at first here. And we'll look at how to solve some of these problems rather than getting down to exact numerical answers, and kind of keep this quick. So momentum and its conservation is one of the major areas of study of physics. P is the symbol for momentum, and momentum is defined as two different quantities multiplied together, the mass times the velocity. Okay, both the velocity is a vector. We often have an arrow over it. We write it in the equation. And the momentum is also a vector. So we sometimes write them like that with a little arrow over them, or in bold text, a bold font in the textbook, to show that they are vector quantities. So that is how you find momentum of one object. So a really simple example, if a ball is moving along at 6 meters per second and it has a mass of 2 kilograms, you would simply multiply these two numbers together and you would say its momentum at that moment is 12 kilograms meters per second, and it's a vector, so it would point to the right, the same direction the velocity of 6 meters per second is pointing. Another idea within the physics we'll be looking at is called conservation of momentum. It's very similar to conservation of energy, which is why these two topics are kind of linked in homework assignment 5. The law of conservation of momentum just tells us that for a closed and isolated system, that the momentum before anything in the systems collide has to equal the momentum after they collide. You'll hear me say during the year a silly phrase that often helps a student remember to use momentum as a strategy at that point in time, and that is if you see a collision, call the cops. Okay, COPS in this case being an acronym for conservation of P, momentum. Okay, conservation of momentum. So we often write it as a statement simply like this, and it does have a little amendment. It does have to be a closed, isolated system. You can't have some external force acting on the system. So for instance, if there was a wall and someone is standing and leaning against the wall, and they throw something away from them, maybe our ball up here with a momentum of 12 kilograms meters per second, okay, they would not recoil any measurable amount. That is, they wouldn't have any speed backward because they're leaning up against a wall. If we treat the whole person as a single particle, I'm sure parts of their body move backward a little bit when they throw the ball, but their body doesn't move backward because of the wall. So the wall is placing an external force on the person and doesn't let them move backward. So we would say there that momentum doesn't appear to be conserved if we're looking at just the system of the person or the ball only as our system in the problem. However, that's because of that external force. Okay, so if we broadened our system to include the whole building or the whole Earth, we would still see momentum conserved as a whole. And the statement is certainly generally true that momentum is conserved, but if you want to look at a single isolated system, you got to be careful that it's truly isolated and doesn't have external forces, a net external force acting on it. Okay. Now to number 18, and kind of looking at the problem. It's very similar to conservation of energy in its idea. So we look at the momentum beforehand, and so we have a nucleus, right? Beforehand, and then afterward we have an alpha particle plus a thorium nucleus afterward. And so if I look at the momentum of the nucleus, okay, I'm going to call it the P of and the nucleus, and I'll say it equals P of my alpha plus P of thorium. So the P's are the momentums. And I'm going to put in a 0 on the left because before this thing recoils, we're going to make a statement that it doesn't have any momentum beforehand. And so it stays in one piece for billions of years, and then it decays. So the alpha particle is spit out at a certain speed, Okay, but beforehand we have our mass of our nucleus, which I'm not even going to put in because it doesn't matter, and its speed is 0. It's just kind of chilling out and sitting there. Then you put in the mass of the alpha particle, it's given in the problem, and you put in the recoil velocity of the alpha particle that it gave us right here as 1.9 times 10 to the 7th meters per second. Okay, multiplying it times the mass of the alpha particle, and that is the momentum of the alpha particle. Okay, and that's going to equal our mass of our thorium nucleus, which is given, times our velocity of our thorium nucleus, which is unknown. So in this problem, I have this one variable right here that's unknown, and all other variables are known. Let's see. Okay, and I found the velocity here to be a negative 3.26 times 10 to the 5th meters per second. The negative here is just because it's a recoil velocity when I plugged in the numbers. It doesn't really matter about the negative sign because the problem did ask you for a speed of recoil. Okay, so that speed of recoil doesn't have a negative sign in it because it's not a vector. Number 19 is a similar problem. There is a gun that is standing. I don't know how a gun stands, but there's a gun standing on a frictionless surface. And if there's a bullet with a muzzle velocity of 313, and you got to watch your units here because one of them is in grams, okay, and one is in kilograms. And so you just want to make sure that you have the same units for everything. It does ask for the answer in kilograms, so we should probably change the grams to kilograms. It wants to know what's the momentum of the bullet after the gun is fired. To get this, you can simply multiply the mass of the bullet in kilograms, right? 0.545 kilograms times the velocity of 313 and get its momentum. Then it wants to know the momentum of the gun. Of course, it's the exact same answer. So whatever answer you get for 19, you can plug it in for 20 as well. One of them would have a negative momentum, and it does tell us the positive direction is that of the bullet. So number 20 would be a negative answer, since it is the gun recoiling backward. Oops. And the next question here asks us about the kinetic energy of the bullet and about the kinetic energy of the gun. Their kinetic energies would not be the same number because the velocity is squared, and 313 squared is a lot bigger than the velocity of the gun squared. And so that factor is going to make the kinetic energy much bigger for the bullet, which is why when the gun backfires or recoils into the person in their hand or their shoulder, it certainly pushes on them, but it doesn't hurt them or kill them. But the bullet obviously has enough energy to kill a person. All right, so that is how you would attack this. Again, for the kinetic energy, it gives you the mass and it gives you the velocity. So we're just looking at the mass of the bullet times, the velocity of the bullet squared, and you would divide it by 2, right? To find its kinetic energy here. The kinetic energy of the gun, you got to be a little bit careful, and you're going to have to use your momentum down here, and you have to divide it by 28 to find the velocity. All right, so the velocity of the gun before you do kinetic energy would be the momentum you found divided by its mass of 28 kilograms. And that would give you the velocity you could plug in to find kinetic energy. Next question here is asking about a softball that's being pitched at a certain speed. The batter hit it directly back at an even faster speed of 21 meters per second. And it gives you a time of interaction of 15 thousandths of a second, and wants to know what's the magnitude of the impulse imparted to the ball. So let's take a look at impulse and how it is related to momentum. It is a slight extension here from what we've already discussed, but not too much at all. Newton's second law can be rewritten a little bit differently. And instead of writing it as MA, we can write the A in an algebraic form of the change in the velocity over the change in time. And from here, we can multiply both sides of the equation by change in time. And we can say that the net external force times the change in time equals the mass times change in velocity. And the quantity on the left-hand side is defined in physics as impulse. Okay, so it's given the symbol J, a capital J typically, and so impulse is that average net external force multiplied times the time. We'll be using a calculus version of that later in the year, but not today. And on the right-hand side, we say we have m times change in v, which is usually phrased or said out loud as the change in the momentum. So m times v would be momentum. This would be the change in momentum. So we have something here called our impulse. That's this side of the equation. And over here is our change in momentum. So we'll call it our impulse momentum theorem, that little statement that is in blue, that the net force times the change in time equals mass times change in velocity. All right, so let's go ahead and take a look at this little softball problem. In this softball problem, it wants to know what is the impulse given to the ball. And in these problems, you either have enough information to solve for the left-hand side or the right-hand side right away, but usually not both. So as we look at our problem, we look at the given quantities in this problem. I see I have a mass in kilograms. I have a speed after the ball is hit and a speed before the ball is hit. Okay, so that's going to give me three things that I know: mass, VI, and VF. It's pretty obvious to see, looking at the equation, what kind of information we're given. We're given the right-hand side of the equation, and when we find that, since it equals the impulse, we found the impulse. Okay, so we can say that J, the impulse, is going to be equal to 0.57, that's kilograms of mass, and times our change in velocity. We do want to be careful here. When we do change, we do final minus initial. Okay, final minus initial. We also want to be careful of the sign that we put on the initial velocity. Okay, and let me explain that just for a moment. So when playing baseball, if the baseball comes in one direction at 19 and then the baseball is leaving the other direction even faster at 21 meters per second, then these two arrows point opposite directions, left and right. One of them is going to have a negative sign. It's arbitrary which one I chose to be negative. I just chose the minus 19 to be negative, so I'd have a positive answer in the end. But we multiply this through, and I see that my change in velocity is actually 40. Some people make the mistake and think it's 2. They do 21 minus 19. But in order to go from 19 in one direction to 21 in the other direction, you have to change by 40. Some students can see that more clearly when just simply looking at a number line like so. And here is 0, and here is 20, and here is minus 20. And if you were to actually take steps along this number line from minus 19 here, and you were to take all the steps from minus 19 all the way over to 21, it'd be 40 steps or 40 increments along that number line going from minus 19 to positive 21. So the change in the velocity is 40. Okay, so you multiply that through, and we get the impulse. I got 22.8. The units are kilograms times meters per second. It's the same as momentum because you're multiplying mass times a velocity there. Let's look at the second piece of this. The second piece of it will involve the time, and the left-hand side, or the impulse side of the equation, wants to know what's the magnitude of the average force. Please note this force here is an average. Typically the force might follow a graph with time that might look like this, okay, where you have a certain time at which the force peaks, and we're not actually going to be finding that force. We're going to treat instead that the force is some average value over the entire time, so that the area of these two shapes, let me change my colors out here, so that the area of this taller shape would be the force times the time. I should label my axes here, and that I want to choose a box with an average force, where this box in green has the same as the shaded area in blue. So the two areas are the same, so that I have the same unit or the same quantity when I multiply force times time, but they're not distributed the same. The reason we're doing the nice boxy one here is so I can find an average, and I don't have to use calculus or any other significant analytical math to figure out something about that force as it changes with time. So let's come back to this problem really quickly, and once again we have our simple equation right here for impulse and change in momentum. Since I already found the right-hand side of the equation there, and I know the change in time right there, I can just divide and find the force right away. Okay, so I'm going to say the force is equal to my 22.8 divided by my time, 0.015 seconds. I got an average force of 1,520 newtons imparted to that softball during that collision there. All right, remember, if you see collisions like that, you're just thinking momentum, you're thinking we got to call the cops, because momentum problems are usually collision problems. All right, next one here, it mentions a specific kind of collision called an elastic collision, okay, and so we have two objects colliding elastically, and it wants to know what is the total kinetic energy of the two mass system after the collision. This is kind of a almost trick answer in some ways. They're asking you to know that in this special condition called an elastic collision, that there is no loss of kinetic energy. So kinetic energy initial equals kinetic energy final. And even though they gave you the velocities of 5.5 and 5.2 before they hit, the total kinetic energy will be available after they hit. We simulate this in class by using magnets between the cars, so they don't actually hit at all, and that way we don't have losses due to sound energy and thermal energy and other things going on. So we can just find the kinetic energy ahead of time, and we will have found the answer. So I would just add up the kinetic energy of these two objects. Don't forget to square your velocities. It's easy to forget. And I put in 2.7. I'm going to stop with the units because I'm running out of space. Actually, I'm just really running out of space there. All right, and you multiply those two together, and you get your kinetic energy, and you're done. Oops. All right. Here again, we have something colliding elastically, which means there's no loss of kinetic energy. And it tells us that one of them overtakes the other. And they hit. In all these collisions, there'll be two things that'll be conserved. Both the momentum and the velocity will both be conserved here. All right, so having thought about it for a moment, I'm going to say let's just skip 28 on the homework. Okay, so we're not going to turn in 28. It is a more advanced problem. We can look at it briefly, but you do not have to turn it in. It will not be on the test. But two objects collide, and their momentums. Let me see. I just worked that. Here we go. Their momentums are equal before and after the collision, which results in the statement below. And also their kinetic energies are equal before and after the collision, which results in the second statement below. You see I have two unknowns here, velocity 1 marked in red and velocity 2 marked in blue. So I have two equations and two unknowns, and I can substitute and solve. And it's a nuisance. There's also a fun little trick, shifting reference frames, you can also do. And you can find the velocity at the center of mass, which is done by finding the velocity of each one, adding them together, and dividing by their combined mass. And it finds the velocity of the system of the two. Then you subtract that from each of the velocities. I'm moving very quickly here. I'm not expecting you to understand this, but just kind of follow a little bit. I subtracted off their velocities, and then I have this little trick of toggling the signs, okay? And this is a trick worth kind of just glancing at, that one of the velocities is kind of negative compared to the center of mass, and this one's positive, this one's negative, and you just flip the signs. So in the point of view or the reference frame where you're moving along with the center of mass, all you have to do is just flip the signs, okay? And then you flip the reference frame again by adding that speed of 35.5, the speed of the center of mass back in, and you get the final answers. So this actually is the final answers if you did solve this system of equations up above without actually having to solve it, which is a quick little way. But it is more work than we're going to be doing on the test over the summer homework. So you may skip 28 and not even turn that one in. Looking at 29, this is a pretty simple collision. And so we have a collision between one railroad car moving at 3.8, and then we have two more railroad cars of the same mass going at 1.9, and they're all going the same way. And wants to know what their kinetic energy is after the collision. These are going to couple. Couple means they're going to stick together. And so this kind of collision also has a name. It's usually called a perfectly, or a completely inelastic collision. And in this kind of collision here, again, we'll take the 2,000 kilograms. I'm leaving off units for space here, times the 3.8, plus I'll add it to two more cars, which have a mass of 4,000 times their speed of 1.9. And altogether, they're going to couple and stick together and become one big fat 6,000 kilogram mass at some final velocity. All right, and that's a pretty straightforward one equation, one unknown that came from, again, from our idea of momentum before the collision equals momentum after the collision. Then we're going to plug that into, hey, what is their kinetic energy? All right, and that's going to be 1/2 times 6,000. We're using the 6,000 kilogram mass because it's after the collision, times our final velocity. Find it there. And don't forget to square it, and that gives their kinetic energy. We're going to skip 30 as well. 30 is a more complicated example again. It's called a ballistic pendulum. We'll actually do it in class later, but we're not going to do it on the homework today. All right. Number 31 here says we have a skateboard coasting along the pavement at a certain speed when a cat drops onto it. So here's just our skateboard coming along. And then after it has a collision, it is a skateboard moving along, okay, with a cat on it. And our little cute cat there. And so the cat is going to cause the skateboard to slow down, because the skateboard is going to make the cat speed up, and the cat will have an equal opposite reaction, causing it to slow down. So we can take the momentum that is there before the collision occurs, massive skateboard times speed of skateboard. It's a pretty fast skateboard there. Okay, and we can then look at their completely inelastic collision again, or perfectly inelastic collision where these two stick together, and add up the masses. It looks like it's 1.598 kilograms times their final velocity together. And so you set those two terms equal to each other, divide both sides by their mega mass or combined mass, and we end up with the final velocity. Okay, so that is the second half of the set on momentum. Again, 28 and 30 you can skip. Most of the others were worked here, so please be ready for the test on Friday, and I will catch up with you then.